Ever get that feeling that the world's just throwing information at you? And the first big challenge is just understanding what it all even means.
Oh, definitely.
Really boils down to having some shared way to describe, what's going on around us.
Absolutely. I mean, just think about trying to build anything complex, right? Like a bridge.
Or a computer chip, yeah.
If everyone had their own private way of measuring and describing its parts, it would be, well, utter chaos.
Which is exactly why we're taking a deep dive today into something really foundational, physical quantities and their units. We've got two great resources here to sort of unpack this. First, there's a transcript of a really clear YouTube video by Standa Jakubek, it's originally in Czech, called Fyzikalny Velčiny Jednotky. And there's also a PDF that goes along with it.
Right.
Now, this material, it was originally put together for technical secondary school students, but honestly, it's gold for anyone who wants to get a really solid handle on these basic physics concepts.
Yeah, these sources, they have this knack for taking what can sound like a very academic subject.
Yeah, I kind of try sometimes.
And making it surprisingly accessible. They really break down the core ideas in a logical way.
So our mission for this deep dive is pretty straightforward. We want to understand why. Why do we even bother with physical quantities and units in the first place?
Good question.
Then we'll explore the different types that exist, and finally we'll get comfortable with those handy prefixes, like when you talk about a kilometer versus, say, a meter.
Kilo, mega, giga, that stuff.
Exactly. Think of this as building a super strong base for understanding pretty much anything scientific or technical down the line. And don't worry, we're going to keep the technical jargon to a minimum.
We'll try our best.
Okay, so let's jump in. What exactly are physical quantities? What are we talking about here?
Well, as our sources point out, physical quantities serve a really fundamental purpose. They let us describe the state of physical objects.
Okay.
And that could be anything from, a solid thing you can touch, like a rod.
Right, to something less tangible.
Right.
Like a magnetic field, or even a dynamic event, like a lightning strike.
Right. The transcript gives some really helpful examples to kind of wrap our heads around this. We're talking about something as simple as the length of a stick that describes a key property of the stick itself, or the temperature of a liquid that tells us about its thermal state, how hot or cold it is.
Yeah.
Then you have the duration of an event, like how long does it take for a kettle to boil, or the speed of movement, how fast is that train going. These are all measurable aspects of the physical world.
Exactly. And the PDF gives us a nice sort of formal definition. Physical quantities are properties of physical objects that we can measure and, this is crucial, express using a number.
Ah, the number part.
The ability to put a number on it is what sets them apart.
Ah, yes. The transcript uses a really relatable example here, the taste of goulash. Now, if you've ever had a good goulash, you know the taste is a pretty defining characteristic.
Absolutely. It's what makes a goulash, you might say. But, as the source points out, it's tough to imagine inventing some kind of device, like a tastometer or something,
Right.
to objectively measure that taste and say, okay, this goulash has a taste value of 7.2. We can describe it maybe as smoky or savory, or,
You can describe it qualitatively,
but not in a way that everyone would agree on with a specific number.
and that's the key distinction. Lots of things have qualities or properties, sure, but for a property to be a physical quantity, we need to be able to measure it and get a numerical value.
Right.
That's what allows us to be precise and to really communicate those properties effectively to others. So if you can measure it and get a number, you're likely dealing with a physical quantity.
Okay, so we can measure these things and get a number, but how do we actually do the measuring? How does that work?
Well, our sources explain that at its heart, measurement is really an act of comparison.
Comparison. Okay.
We're taking the quantity we want to measure and comparing its size to a chosen unit of the same kind. Think back to that example in the transcript of measuring the length of a classroom wall.
Right. I can picture someone walking along the wall with like a meter stick, laying it down end to end.
Exactly. That meter stick has a certain length, right?
Yeah.
And we've all agreed to call that length 1 meter. So the act of measuring the wall is simply seeing how many of those 1 meter lengths fit along it.
That makes perfect sense. It's about seeing how many of our chosen chunks, the units, fit into whatever we're trying to measure.
Precisely.
And from this idea of comparison, the sources give us a general formula for how to express a physical quantity.
Yes, the formula is pretty straightforward but incredibly important. A physical quantity is equal to a numerical value multiplied by the unit.
Numerical value times unit.
Got it.
The numerical value just tells us how many of those unit chunks we counted.
And the sources give us some clear examples of this in action. Like the length of that rod we mentioned might be 2 meters. So 2 is the numerical value, and meters is the unit. Or the duration of a class, 45 minutes. 45 is the number, minutes are the units. And both the PDF and the transcript really emphasize a crucial point here. That number, the 2 or the 45 in our examples, it doesn't mean a thing on its own without the unit attached to it.
Absolutely. If someone just said, hey, the length is 2, your immediate reaction would be 2 inches, 2 miles, 2
bananas,
2 paper clips.
Yeah.
Without the unit, the number is just floating there, not really telling us anything concrete about the physical world.
Precisely.
Yeah.
The unit provides the context. It's what makes that numerical value interpretable and, useful. So the golden rule is always state your units.
Always state your units. Okay. Now, this brings up an interesting challenge, doesn't it? The transcript uses a really clever analogy here. Imagines 2 people in a forest who each find a straight stick. And they decide, okay, this stick is my personal unit of length.
It's a very easy scenario to picture, isn't it? Each person has a perfectly good unit of length for them. It's their own stick.
Right.
But the obvious problem is that their sticks are almost certainly going to be different lengths.
Exactly. So if they both try to measure the same classroom, one might say it's 15 stick lengths, while the other says it's 4 stick lengths. And suddenly, they can't agree on the actual size of the room.
Yeah, communication breaks down.
The transcript even includes a funny image of Einstein holding one stick and another person holding a completely different one. It really highlights how confusing it gets when everyone's using their own standards.
And what's fascinating here is that this wasn't just like a hypothetical problem. Historically, different regions, different trades, even different people use their own unique systems of measurement.
Exactly.
Oh yeah. This caused enormous headaches for trade, for science, for pretty much any kind of collaboration. Imagine trying to build a ship if the carpenters used one kind of foot measurement and the sailmakers used a different one.
Wow. Yeah, that wouldn't work. The transcript then illustrates this with a list of different ways we can express the same length. You've got meters, centimeters, decimeters, millimeters, kilometers.
Even inches, feet.
Right. It really drives home the point that we absolutely need to be speaking the same language when it comes to measurement.
Absolutely. For meaningful communication about physical quantities, 2 key things are essential. First, we must have a shared understanding of the unit itself. We need to agree on what exactly a meter or a second is.
Okay. Agree on the definition.
And second, as we've already hammered home, we must always include the unit when we state a numerical value.
Right. Got it.
Yeah.
This need for common agreement and clarity is what led to the development of standardized units. And that brings us to the International System of Units, or the SI system.
The SI system, yep. It's essentially a globally agreed upon set of units for all sorts of physical quantities.
Global agreement. That sounds important.
It is. The transcript briefly touches on its history, mentioning the birth of the metric system around 1790 in France.
During the French Revolution. Wow.
Yeah. It's amazing to think that this push for a universal system of measurement happened during such a period of upheaval. It really speaks to the fundamental need for order and agreement, even in chaotic times.
It's interesting that this push for standardized measurement came out of a time of such significant societal change. The transcript even playfully mentions the guillotine in the same breath as this unification effort.
Well, it was a time of radical change, I suppose, but the underlying idea was the same, moving towards a more rational and universal way of doing things.
Makes sense.
The transcript then points out that the modern SI system, as we know it today, was established much later in 1960.
1960. So not that long ago, really, in the grand scheme of things.
Relatively speaking, no. And the importance of the SI system really can't be overstated. The transcript mentions that it's the standard in physics,
Right.
and it's often legally mandated in many countries. It's amazing to think that this globally agreed upon system isn't just about avoiding arguments over measurement. It's the very foundation upon which so much of our modern technology and scientific understanding is built.
Yeah, I mean, imagine trying to coordinate the launch of a satellite if every country used a different definition of a meter or a second.
Exactly. Total disaster.
Okay, so this SI system has been established. What kinds of physical quantities and units does it actually include? How's it organized?
Okay, so the sources tell us that the SI system organizes physical quantities and their units into 4 main categories: basic, supplementary, derived, and auxiliary.
4 categories. Got it.
Yeah.
Let's start with basic.
You're right, the basic ones. The transcript lists 7 basic quantities and their corresponding units. These are like the fundamental building blocks. Everything else in the SI system is built upon these 7.
Okay, the foundations, what are they?
First one is length. The transcript kind of guesses maybe from lint or just length. And the unit is the meter, symbol M.
Length, meter, okay.
Then we have mass, symbolized by M, possibly from an old Greek word for lump, meth, apparently. And its unit is the kilogram.
Mass, kilogram.
Check.
Third is time, symbol T for time, pretty straightforward. And the unit is the second S.
Time, second. Easy enough.
Moving on, we have electric current, symbolized by I. Now, the transcript notes the reason for I isn't actually given in our sources.
Bit of a mystery, maybe. But the unit for electric current is the ampere, symbol A.
Current, ampere. Got it. What's next?
Next is thermodynamic temperature, with the symbol T for temperature. And it's important to emphasize thermodynamic temperature here.
Why thermodynamic?
Because the unit is Kelvin, K. The transcript mentions that the reason Kelvin is fundamental, rather than, say, Celsius, is something you get into in thermodynamics. Think of Kelvin as an absolute scale. 0 Kelvin is, well, absolute 0, the coldest possible temperature where thermal motion basically stops.
Yeah. Okay, so it's more fundamental scientifically.
Exactly. That's why it's a base unit, crucial for certain calculations.
Okay. Kelvin. Next.
Following that, we have the amount of substance, symbolized by N, and its unit is the mole, with the abbreviation mole.
Mole. Okay. Heard of that in chemistry.
Yep. And finally, we have luminous intensity, symbolized by I.
Wait, again, like electric current?
Yeah, exactly. But the transcript makes a really good point here, highlighting that the symbol I is shared with electric current, so context is absolutely crucial to understanding which quantity you're talking about.
Or to know. Okay, so luminous intensity.
Unit.
The unit is the candela, CD.
Candela. Okay, so those are the 7 basic ones.
That's them. And it's helpful, as the transcript points out, that for someone starting out, you probably already know length, mass, time, maybe temperature.
Yeah, those feel familiar.
Then you'll learn about electric current, and then maybe amount of substance and luminous intensity are the newer concepts. Sort of a natural progression.
Right, builds up.
Exactly. And the transcript then moves on to a really fascinating historical note about how these basic units were originally defined.
Oh, yeah.
And how that definition has actually changed over time.
How so?
Well, it talks about the historical use of physical prototypes, or etalons. These were actual physical objects, often made of materials like platinum iridium. Like the standard kilogram was a specific lump of metal kept in a vault.
Wow, a real object. Yeah. But the fascinating thing is the modern shift away from these physical artifacts towards definitions based on fundamental physical constants.
Constants, like the speed of light.
Exactly like the speed of light. The transcript mentions preparations for this change began around 2011, with the new definitions officially taking effect on May 20th, 2019.
So quite recently.
And while it sounds maybe more complicated than having a physical bar in a vault,
Yeah, sounds abstract.
defining units based on these unchanging natural constants ensures a level of accuracy and universality that those physical objects could never quite guarantee. It's about anchoring our measurements to the very fabric of the universe itself.
That's actually pretty profound. The transcript gives the example of the meter now being defined by the speed of light, which is, constant everywhere.
Precisely. It emphasizes that while these new definitions might sound more abstract, they are actually far more reliable and precise in the long run.
Okay, interesting. A trade-off between, intuitive feel and ultimate stability.
You got it. Now, after the basic units, we have the supplementary quantities and units.
Supplementary. Okay, what are those?
The transcript tells us there are just 2 of these, and they both relate to angles.
Angles, okay.
First, we have plane angle, often represented by Greek letters like alpha, beta, gamma,
Yeah.
The unit for plane angle in the SI system isn't degrees, which we might use more often day to day.
Right, 360 degrees in a circle.
But the radian, with the symbol rad.
Radian, how does that work?
The transcript uses a really helpful circle analogy. Imagine you have a circle with a radius r.
Okay.
If you measure an arc along the curved edge of that circle, that is exactly the same length as the radius, so length r. The angle formed at the center by the 2 ends of that arc is defined as 1 radian.
Ah, okay, so the arc length equals the radius length.
Exactly. It's a very natural way to measure angles in mathematics and physics. Think about describing how much a wheel turns, maybe.
Right. The transcript also mentions the relationship to pi, noting there are 2 radians in a full circle.
Correct. And it points out we'll bump into radians again in trigonometry and when discussing circular motion. So good to know.
Okay, one down. What's the second supplementary one?
Second one is solid angle, symbolized by the Greek letter omega.
Omega. Okay.
The unit for solid angle is the steradian.
Steradian. Okay, how do we picture that? Plane angle was a circle.
Solid angle is more like a sphere. Imagine a cone extending out from the center of the sphere.
Like an ice cream cone shape.
Sort of, yeah. And this cone intersects the surface of the sphere, carving out a little patch of area on the surface.
Okay.
If that area on the sphere surface is equal to the square of the sphere's radius, so r,
Radius squared.
then the solid angle of that cone, how pointy it is defined as 1 steradian. You can think of it as measuring a chunk of 3D space, like how much of your field of view an object takes up.
Okay, that's a bit harder to visualize maybe.
Yeah.
Where is it used?
The transcript mentions it's particularly important in photometry dealing with measuring light, like the intensity of a light bulb in different directions. And it says it's probably something covered in more advanced studies.
Gotcha. So less common maybe, but important for specific things like light.
Exactly. So basic units, supplementary angle units. What's next?
Next up, we have the derived quantities and units.
Derived. Okay, sounds like they come from the others.
Precisely. The transcript explains that these are, as the name suggests, derived from the basic and supplementary units using defining equations.
Defining equations, like formulas.
Yeah, the mathematical formulas that link different physical quantities together. The sources give us a whole bunch of examples of derived quantities, many we've probably encountered. Things like density,
Mass per volume,
speed,
existence over time.
force, electric voltage, electrical resistance, acceleration, even just path length, like the total distance traveled.
Okay, familiar concept. So how do we get the units for these?
This is the neat part. The transcript lays it out very clearly.
Yeah.
We determine the units of derived quantities directly from their defining equations.
Ah, from the formula itself.
Exactly. They use the familiar example of speed. We know speed is defined as distance traveled divided by the time it takes.
Distance time.
So to define the unit of speed, we simply take the unit of distance, which is the meter m, and divide it by the unit of time, which is the second m, giving us meters per second, or m's.
Or MESU, same thing.
Right. Meters per second makes sense.
Exactly. The transcript then works through a few more examples just to really solidify the concept, like volume. For a simple cube, volume V is the length of one side, A, times itself 3 times A.
Length times width times height, basically.
Right. Since the unit of length is the meter m, the unit of volume is meter times meter times meter.
Meters cubed.
Perfect.
Yeah.
Similarly, for area, say a square, area A is side length A times itself, A.
The unit is meters squared,
Yeah,
MO.
you got it. And one more. Density, which is defined as mass, m divided by volume, V.
Mass over volume.
So the unit of density is the unit of mass, which is the kilogram, kJ,
Right.
divided by the unit of volume, which we just found is cubic meter, m. So kilograms per cubic meter, kilog, mag.
Okay, it really does just flow from the definition and the basic units.
It's really quite elegant, isn't it? The transcript emphasizes this fundamental simplicity. The units of these more complex quantities flow directly and logically from the units of the basic ones through their defining relationships.
Yeah.
It's a pattern you'll see again and again as you explore more of physics. It shows how interconnected everything is within the SI system.
Cool. Okay, so that was basic, supplementary, derived.
Yeah.
What's the fourth category?
The fourth category is auxiliary units, or as the original Czech transcript says, vedlejší, which kind of means secondary or side units.
Auxiliary. Okay. How are these different?
These are interesting because the transcript explains that these units aren't officially part of the core SI system,
Not officially SI.
but they are used so widely in everyday life and in certain fields that their use is permitted alongside SI units.
Okay. Like what? Give me some examples.
Think about units we all use constantly. For time, day, minute, hour, year, those aren't the base SI unit of the second, right?
Right. We don't usually talk about years and seconds.
Exactly. Also, degrees Celsius for temperature, for huge distances in space. Light year, astronomical unit, parsec. And even for angles, we often use angular degrees, minutes, and seconds, not just radians.
Okay, yeah. Those are all super common. The transcript uses a fun example here, imagining someone saying they enjoyed their 172,800 seconds long weekend.
Huh, While technically correct, 2 days is 172,800 seconds.
Nobody talks like that.
No, saying 2 days is just much more convenient and easily understood in everyday conversation.
Definitely.
So these auxiliary units often make communication much simpler in specific contexts. However, and this is important, the transcript makes a really key point. When you're actually doing calculations in physics or engineering, it's very often necessary to convert these auxiliary units back into the corresponding SI unit.
So convert days to seconds or Celsius to Kelvin, maybe?
Exactly. To make sure your equations work correctly and consistently within the SI framework. This is something we'll likely see emphasized in specific examples later on.
Okay, good to keep in mind. So 4 types of units covered. Now the transcript moves on to another important way of classifying physical quantities. Scalar versus vector quantities. What's the main difference here?
The key difference, it really boils down to whether a quantity is fully described by just its size, its magnitude, and a unit.
Okay, size and unit.
Or if it also has a direction associated with it.
That's direction matters for something.
Exactly. All physical quantities have a magnitude and a unit. Scalar quantities are complete with just that information. Vector quantities need that direction part to be fully understood.
Okay. Can you give examples of scalars?
Sure. The transcript lists things like energy, density, pressure, time, mass, and it asks a really helpful question about energy. Does it even make sense to talk about 300 joules in that direction?
No, not really. Energy is just energy.
Right. Direction isn't a relevant aspect. For scalar quantities, the number and the unit tell the whole story.
Okay, so what about vectors then, where direction does matter?
For vector quantities, the transcript provides examples like force and velocity. In these cases, knowing the direction is absolutely crucial.
How so?
Well, saying a force is 20 newtons isn't enough information, is it? We need to know if it's pushing up, down, left, or right to understand its effect on something.
Right, a push to the right is different from a push down.
Exactly. Similarly, a velocity of 20 meters per second only tells us how fast something is moving.
It's speed.
But not where it's going. Is it going north, south, up, down? That direction is part of the velocity.
Okay, that makes sense. Force and velocity need direction. And the transcript also explains how we visually represent these different types when we write them down.
Yes. For scalar quantities, we just use regular letters, like P for pressure, T for time, for density. Simple.
Okay.
But for vector quantities, the standard way is to write the letter representing the quantity with a small arrow drawn above it, like with an arrow for force, none with an arrow for velocity, no with an arrow for acceleration.
The little arrow means this has direction.
Precisely. The transcript also mentions that in older textbooks, you might see bold letters used instead of the arrow. That was often just due to printing limitations back then.
Okay. Bold or arrow means vector. Now, what if we only care about the size of the vector, not the direction?
Good question. If we're only interested in the magnitude of a vector quantity, just its size, we write the symbol without the arrow.
So just D instead of dumb with an arrow.
Exactly. The transcript uses a relatable example. If a police officer stops you for driving 80 kilometers, for the purpose of the speeding ticket, they usually don't care about the direction you were traveling. Only the magnitude of your velocity, your speed matters.
Right, 80 kilometers is 80 kilometers no matter if it was north or south.
Exactly. So in that context, we would just talk about the speed v as 80 kilometers without the arrow.
Yep.
The transcript emphasizes it's really important to be consistent with this notation to avoid any confusion when dealing with physical quantities. Use the arrow when direction matters, leave it off when only magnitude matters.
Got it. Scalar vector notation. We're building a really solid foundation here. Now let's talk about those prefixes, the kilos, millis, and everything in between.
Yes, the prefixes. Very useful.
The transcript asks a really practical question.
Yeah?
Can we write very large or very small numbers in a more concise way? And the answer, thankfully, is yes.
Absolutely. Dealing with numbers that have just a long string of zeros.
Yeah, like 0.000, lots of zeros, 1.
It can be not only cumbersome, but also really easy to make mistakes with. The transcript mentions the limitations of calculator displays as a prime example. Imagine trying to type in 0.0000000000000 accurately every time.
You probably miss a zero somewhere.
Easily done. That's where prefixes come to the rescue. The transcript introduces them as a clever way to express multiples and submultiples of our base units, making these enormous or tiny numbers much more manageable.
Okay, so they're like shorthand.
Pretty much. And it lays out a comprehensive table of these prefixes. On the larger end, multiples, we start with kilo K for 10 ep or 1,000.
Kilo, like kilometer.
Then mega M for 10 arrow, a million. Giga G for 10 euro, a billion. Tera T for 10 euro, a trillion. Then it gets bigger. Peta P for 10 euro, a set E for 10 euro.
Wow.
Dot Z for 10 euro, Yoda Y for 10 euro. And then the more recently added ones, Rana R for 10 euro and Quetta Q for 10 euro.
Rana and Quetta. Never even heard of those.
They're pretty new. Added in, I think, late 2022. Shows how science keeps pushing boundaries.
Okay, so those are the big ones. What about the small side, submultiples?
Right. We have milli M for 10 euro, 1,000. Micro, that's the Greek letter mu for 10 euro, 1 millionth. Nano N for 10 euro, 1 billionth. Pico P for 10 euro, 1 trillionth.
Milli, micro, nano, pico. Hear those a lot in tech.
Yep. Then it gets even smaller. Femto F for 10 euro. Eto A for 10 euro, Zepto Z for 10 euro, Yocto Y for 10 euro, and again, the new tiny ones, Ronto R for 10 euro and Quecto Q for 10 euro.
Ronto and Quecto. Wow. It's mind-boggling how small that is. And interesting, like you said, that these really big and small ones are recent additions.
Yeah, it reflects the need to describe things at scales we couldn't even measure until relatively recently. Now, how do we actually use these prefixes? The transcript gives us some really clear examples to work through.
Okay, let's do it. Example 1.
First one. 0.25 kilonewton, that's kilonewtons. The K prefix stands for kilo, which means 10, 11, or 1,000.
Right.
So 0.25 kilonewton is the same as 0.25 multiplied by 1,000 n newtons, which equals...
250 n. Move the decimal 3 places right.
Exactly, 250 n. Simple enough.
Okay, next one. 2110 milligo megawatts.
Mega M represents 10 A or 1 million. So 2110 milliW becomes 2110 multiplied by 1 million W watts.
Okay, that's 2110 with 6 zeros after it. No, wait. Move the decimal 6 places right from 2110.0, so 2,110,000,000 Ws. 2.11 billion watts.
Perfect. 2,110,000,000 watts. Now for a smaller unit, 1.2 PF picofarads.
Pico, that was tiny. 10 horn.
That's the one, 10 to the power of negative 12. So 1.2 PF is 1.2 multiplied by 10 euro F farads to write that out.
Okay, move the decimal 12 places to the left, so 0.11 zeros, then 12F.
Exactly. 0.0000000000000000000000012. Okay, another small one. 0.1 nanometers.
Nano N is 1000, so 0.1 nanometers is 0.1 multiplied by 10 in meters.
9 places left from 0.1, so 0.8 zeros, then 1 meter, 0.000000000000001 meters.
Spot on. And one more in the smaller range, 25.6 to now microamperes.
Microamperes, 10, you know.
So 25.6 to is 25.6 multiplied by 10 AA amperes, 6 places left.
Gives us 0.0000000C56A.
Perfect. Finally, we have that really big one, 6RG ronogram.
Rana R, the new one, 10 RG. Right, so 6RG is 6 multiplied by 10 by entry G addergrams. That's a 6 with 27 zeros.
Whoa.
Now, the transcript adds that really interesting bit of context here, converting this to kilograms. Since there are 1,000 grams in a kilogram, that's 10 milligrams, 0.6 octenary is the same as 6 by 10 kilograms, removing 3 powers of 10.
Okay, 6 times 10 to the 24 kilograms. Still a huge number.
It is, and here's where it gets really interesting. The transcript points out that the approximate mass of the entire Earth
The whole planet.
is around 6 times 10 bios, or 6 times time AG. 6 ronograms.
No way. So 6RG is roughly the mass of the Earth. That's incredible.
Isn't it? It really puts into perspective just how mind-bogglingly large these prefixes can get and why they're so essential in fields like astronomy when we talk about the masses of planets and stars.
Yeah, it gives you a real feel for it. That's a fantastic example.
It really connects these abstract prefixes to something tangible. Well, planet-sized tangible. Now, the transcript also mentions that there are a few other permitted prefixes that aren't strictly powers of 1,000.
Ooh. Which ones are those?
Yes, these are prefixes that represent multiples or submultiples of 10, but aren't specifically 10 meter, 10 imatero, etc. The table in the source includes deca, de for 10 in air.
Yeka, like decagon.
Kind of, yeah. Hecto, H for 10 minute or 100. Deci D for 10 ear or 1/10, and centi C for 10 ear or 100th.
Deci and centi, we use those all the time. Deciliter, centimeter.
Exactly. These are prefixes we encounter quite often in everyday life. The transcript gives the example of maybe buying 10 decagrams of salami at the deli.
Which is 10 times 10 grams, so 100 grams.
Right. Or maybe a recipe calls for 2 dl deciliters of wine.
2/10 of a liter, so 0.2 valve.
Yep. And of course, we see centimeters all the time on rulers, where a centimeter is 1/100th of a meter. Hecto is less common in the US, maybe, but you hear hectoliters, HL, for large volumes of liquid sometimes, like beer production 3 HL is 300 L.
Okay. The transcript runs through a few quick examples too, right?
Yeah, just to reinforce, 2DLL is 2DM10LO, which is 0.2 elts. 38HL is 38L10 beta L, or 3800L. And 15.4 centimeters is 15.4 at 10 kilometers, which equals 0.154 meters.
Okay. So why are these allowed if the main ones jump by thousands? Just because they're common?
Pretty much. The key thing to remember about these is that while the preferred SI prefixes jump by factors of 1,000 kilo, mega, milli, micro, these others are still permitted because they're so ingrained in our common usage and can be very practical. Like you said, the centimeter on a standard ruler is super convenient.
Makes sense.
However, for precise scientific work, you might still need to convert these to the base SI units or to the power of 1,000 prefixes just for consistency in your calculations.
Okay, good tip. Wow, we have covered an incredible amount of fundamental information in this deep dive. Let's take a moment to quickly recap the key things we've explored.
Absolutely. Good idea. So we started by understanding the fundamental importance of physical quantities and their units
Why we need them.
for describing the world around us and just enabling clear communication. We looked at how measurement works basically as a process of comparison.
Comparing to a standard unit. And we stressed why you absolutely must always include the unit with any numerical value. 2 means nothing without 2 what?
Exactly. Then we moved on to the critical need for standardized units to avoid confusion and enable collaboration. That led us straight to the International System of Units, the SI system.
The global standard. And we explored the 4 main categories within SI. The 7 basic foundational units.
Length, mass, time, current, temperature, amount of substance, luminous intensity.
The 2 supplementary units for angles, radians to radian. The derived units that come from combining the basic ones using formulas like speed or density.
Right, their units come from the formulas too.
And those auxiliary units that are permitted just because of common use, like hours, degrees Celsius, centimeters.
Yep. We also highlighted that essential difference between scalar quantities,
size and unit only, like mass or energy,
and vector quantities, which also have a direction, like force or velocity. And we talked about how we represent those in writing with the little arrow for vectors.
Right, the arrow notation. And finally, we dove into the world of prefixes, understanding how they allow us to express incredibly large and incredibly small values in a much more manageable way.
Kilo, mega, giga, milli, micro, nano, and even rana and quecto.
And we worked through a bunch of examples of how to convert between prefix units and the base units, moving that decimal point around.
Understanding these fundamental concepts really is key. It provides the essential groundwork, the toolbox really, for delving deeper into the fascinating world of physics and, frankly, all other scientific and technical fields.
Definitely. So as you go about your day, maybe take a moment to think about just how many aspects of your life rely on these standardized measurements. I mean, everything from the technology you're using right now,
the phone, the computer,
to the food you buy at the store, weighed in kilograms or pounds perhaps, it's everywhere.
It really is.
What would a world without these shared definitions even look like? It's a really thought-provoking question, isn't it? It highlights the importance of this seemingly basic but absolutely crucial system we've been talking about.
Makes you appreciate that little kg symbol on the flour bag a bit more.
Exactly. Maybe we'll even inspire you, the listener, to explore a bit more about the history of measurement, which is fascinating, or maybe a specific scientific field that relies heavily on these concepts. There's always more to learn.